Okay, so good morning and let us start today's class. See, we were discussing about the deflection calculation in beams using which method? Macaulay's method. Okay, and basically it is nothing but double integration method. And in the Macaulay's method, you have seen that if there are multiple concentrated loads, right? Then you will have, actually if you want to solve it using double integration method, direct double integration method, then what will happen? You will get multiple number of constants, and for that you need to have multiple number of boundary conditions, which is very difficult to get. And using Macaulay's method, we have seen that if we can develop a generic equation for the moment, considering the section X is being put at different locations before the load and after the load, then we get one equation, and in that equation, what is the assumption in the Macaulay's method? If the terms becomes negative or 0 after putting the value of x, then it will be negative. That is the assumption. Okay. So now we have solved in the previous class, we have solved a problem on multiple concentrated load. Now if there is a uniformly distributed load, UD, and a concentrated load, then how to approach for that problem. Okay, that we will discuss in today's class. So we will take up the problem and we will see why this method of deflection calculation is so important in case of analysis of beams as well as analysis of structure. We will understand through this problem. See, what we have taken till now, the problems were structurally determinate problems, right? Beams were structurally determinate, right? Now today we will take up one example for a structural indeterminate. Okay? And for that we will be considering, let us say, we will be considering a cantilever beam. We will be considering a cantilever beam. Let's say we are having a cantilever beam, something like this. Okay, and that cantilever is supported at its free end. Okay, with a roller or let's say maybe a pin. So which kind of cantilever this is called? This is called a propped cantilever. This is called a propped cantilever, right? And this is not a determinate structure, because you see a cantilever beam is a determinate structure. You have three reaction components, or you can say if you neglect the horizontal reaction component, then you have two reaction components, and you have two equations of static, right? So, however, in this case, what you will have? You will have, there is a vertical reaction will come. This is unknown. There is another one reaction which I can neglect. This reaction I can neglect because horizontal forces doesn't come as such if there is a vertical location in the structure, and there will be moment in the structure, as well as there will be a vertical reaction at the supported end. What is this end called? This end will be called prop end, right? This will be called as prop end, and this cantilever will be called as what? Prop cantilever, right? So prop cantilever, if you see, it is not a determinate structure. It is 1 degree indeterminate structure. 1 degree indeterminate, right? Why it is 1 degree indeterminate? You can, if it is a cantilever, then you can solve this and this using equation of time. But this reaction you cannot solve using equation of time. Okay? So now you will see that how the deflection, method of deflection can be used to find out the prop reaction. That means you can solve the integral structure using the equation which will be available for the deflection calculation. Have you understood? And this kind of equations are basically called compatibility conditions. That means the structure will be compatible enough when it is subjected to different loading conditions. So you see, in this case of compatibility, you see what will happen at this point when it is a prop end. What will happen at that point? So if I see from the deflection point of view, then at the prop end, as there is a roller support, or let's say there is a pin support, there will be reaction coming upward and there cannot be any deflection over here. So that is another one condition which will be treated here as a compatibility condition, and that can be used to find out what is the reaction at the problem. So the problem here is, for this cantilever beam, let us say this beam is loaded with a typical loading, as I have told you, that uniformly distributed load. So let's say this beam is 4 meter long. So total beam length is, let's say, 4 meter. Okay? And at every 1 meter, after 1 meter distance, a uniformly distributed load starts, and it is of length 2 meter. Okay? It is of length 2 meter. So that means what I will say, this length of the uniformly distributed load is 2 meter. So how much will be this length from here to here? This is actually 1 meter, and this distance will be 1 meter, right? Correct or not? Is it clear? And then along with this uniformly distributed load, at the middle of the beam, so at the middle of the beam means here, right? So at 2 meter from this, there is a concentrated load also acting on the beam. Okay? And that load is, let's say, 5 kilonewton. And this load, whatever UPL is acting, this is 6 kilonewton per meter. Is it clear? Problem is clear? Now, 5 kilonewton? Point load. This is concentrated load. Concentrated load acting at the middle of the beam. That means from here to here, the distance is from here to here. How much is distance? 1 meter. From here to here, 1 meter. From here to here, 1 meter. From here to here, 1 meter. So beam is divided, let's say, in 4 parts, right? So concentrated load is acting. Concentrated load of 5 kilonewton is acting at the middle of the beam. Now the question here is, find out the load or the reaction at the drop end. So you have to find out what is the reaction R actually coming at this drop end, right? This is the first question. And the second question is, find the maximum bending moment in this structure. Find out the maximum bending moment in this structure. So you see, basically, if you can find out the reaction at the drop end, then what you are doing? You are solving an indeterminate structure. Okay? And what we will use here? We will use the integration method or Macaulay method specially to solve this problem. So let us, how will you approach? So you see, if I now want to approach this problem for solving using Macaulay's method, then what I will do? I will replace this with a reaction, let's say, reaction or load, let's say P. Okay? So if I replace this with the load P, then what I have to do? I will have to write down now the equation of deflection, right? And equation of deflection, what is actually, if you remember, what is the equation of deflection? EI d2i dx2, isn't it? EI d2i dx2, and from where to where I take x? So I will take x from here. So x will be from this direction. Left to right I am taking the x. Clear? Is it clear? Now you tell me what will be the moment equation for this. EI d2i dx2 is equal to m. What is it? EI d2i dx2 is equal to m. Now what will be the moment equation? So if I go on taking sections at different positions, right? So what will be the moment equation over here? So you see, for point load it is not difficult, right? So I take any section anywhere. So let's say if I take any section over here x, or if I take any section over here x, or I take any section over here x, or I take a section over x. So what will happen? Finally you see the moment due to this P at this section, this section, this section, this section, whatever you go, it will be multiplied by P into x. Nothing else. Correct? Also for this load, this 5 kilonewton load, what will be the moment? So if I go beyond this, then moment will come for this. So in case of Macaulay method, general moment equation I will develop. So for that general moment equation, what you have to have? So from here to here the distance is 2 meter. So So how much will be the remaining distance where I will be taking x minus 2. So 5 into x minus 2, that will be the moment because of this 5 kg. Now how will you consider the uniformly distributed load for taking the moment? That is what is the point of question over here, right? Because section x you will be taking at any point, right? Section x you will be taking at any point, correct? So for that, so let us say for to solve this in a very easy way and to write the moment equation in an easier way, what we can do, let us say, what I can say to easily write the equation, I can say instead of this 2 meter load, let's say my beam is loaded with 3 meter. Let me say that beam is loaded with 3 meter load. So another 1 meter load I am adding over here. So if I add this way, then what I should do? I should apply another one load in the reverse direction, right? So what I should do? I should apply another one load of the same intensity in the reverse direction. Is it clear now? Is it clear what I have done for UPL? Have you understood? Suppose I put a load of 5 kN at some place and in the reverse direction I put a load of 5 kN. How much will be the resultant load? 0. So what I have done? I have done this load, I have added a 6 kN per meter load. I have added a 6 kN per meter load over here. And I have in the reverse direction, I have put a 6 kN per meter load. So how much will be the intensity for this load? It will be equal to 0. Why are we doing it? To take the moment equation in a simpler way. Otherwise, the moment equation will get complex. So in case of a UDL problem, if the UDL is not distributed throughout the length of the beam, you understand? Here the UDL is not distributed over the throughout length of the beam. It is distributed at a half length of the beam or some portion of the beam. So in that case, if you want to approach this problem with a single x location and x coordinate, or what should I say, the cross section where I am taking in the horizontal direction, at that point, if I want to consider, I should load it throughout and then I should apply, to nullify, I should apply a reverse direction. This is the approach. If you follow, then problem will become simple. Other than that, this problem is same as we have done it for the point load. Okay? Now you tell me what will be the moment equation. So for this, P, I will be having, if the Px, right? Now this if I take anti-clock, this if I take positive, then because of this UDL. So this UDL is how much distance it is there? So if I take any section over here, so UDL is of length what? Consider the total UDL, not the 2 meter distance. So total UDL length is how much? 3 meter. So if I take any section X, then what will be the length of the UDL? If I take any section X, let's say if I take any section X over here, 3 minus X or X minus 1? X minus 1, because where from X starting? X is starting from here. This is your 0. So from here to here, if this distance is X, so how much will be this distance? This distance will be X minus 1. Is it clear? So how much will be the moment? So if this is positive, this will be negative, right? This way, this is making the moment in this way. So the next moment will be 6 into X minus 1. How much it will be? 6 into X minus 1 whole square by Wx square by 2. Right? If UDL is W, distance is X, then what is the moment? W into X is the load which will be acting at the center. What distance? X by 2. So W into X square by 2. Now here what is X? Value of X is equal to X minus 1. Have you understood? Is it clear to everyone? Okay? Now, another one UDL, you see, we have considered now this UDL, okay? Now you see, if I take a section, if I take any section, let's say over here, so what will be the moment? P into X is the moment over here. You understood what I am saying? So P into X is the moment minus, for this load it is minus 6 into X minus 1 whole square by 2. Now, this reverse direction UDL you have put, right? So that will also create moment. So how much will be the distance from here to here? So this distance is 1 meter and this distance is 2 meter, right? Because after 2 meter you have applied a reverse direction load. So how much is the distance from here to here? This is 1 meter, and from here to here this is 2 meters. So 3 meter, right? And it is applied in the reverse direction. So the moment will be positive because like this P will act. So how much is the load will come? So this load is again plus 6 into X minus 3 whole square by 2. Have you understood why it is coming X minus 3 whole square by 2? Is it clear to everyone? So now you see, now what you have done? You have taken care about the UDL using this double integration method or Macaulay method. What you have done? You have done, instead of this load, you have extended it to the fixed end and then you have put a reverse load and you have considered both the moments because of it. And so, the final loading, the equivalent load is now acting, or the moment because of the equivalent load is what? That load of 6 kilonewton per meter which is acting over a 2 meter length. Is it clear? Now any other moment equation in the moment it will come? Any other value will come? Point load. So we have not yet considered point load. So point load is what? 5 kilonewton. So it is simple. How much will be the value? So this will be positive or negative? This will be also negative. Downward. So this is acting itself. So negative. So how much will be this one? Minus. Tell me. 5 into how much it will be? Minus 5 into X minus 5 into X minus 1 or 2? From here to here 1 meter. From here to here 1 meter. So X minus not 1. Okay? So it's simple geometry. You have to understand about geometry. That's all. You have understood? Clear? Now the next steps are very simple. So now you see in this equation P is your unknown, right? This P is your unknown. Because P is the reaction at the drop end, right? Or R is the reaction. If you take R, then Rx it will come. So P is the unknown at your drop end, right? Now what will be the next step? We are following Macaulay method. So we will be, or we are considering the double integration method. So you integrate. So the first integration will give what? EI dy dx. This will give you what? It will give you p x square by 2. Correct? Minus what will come? 6 into x minus 1 whole cube by 6 plus 6 into x minus 3 whole cube by 6 minus 5 x minus 2 whole square by 2. Clear? Anything else will come? Plus this one. So there will be a constant of integration. Don't forget. If you forget this, then problem will go wrong. Clear? Have you understood? Next. Second integration we will do. So EI y is equal to P x cube by 6 minus. What will be there? So this 6 cancels, right? This 6 cancels, right? And this 2 divided by 5 divided by 2 will give you 2.5. Correct? So now I integrate. So this will give you px cubed by 6. This will be how much? X minus 1 whole to the power 4 by 4. Correct? Plus x minus 3 whole to the power 4 by 4. Correct? Minus 2.5 x minus 2 whole cube by 3 plus C1x plus C. Is it clear? Have you understood? So, two integration, double integration method, 2 times you have done. Now what is the next step? Now you have to apply boundary condition, right? So what will be the first boundary condition? So what I do, I erase this part, okay, and then again redraw maybe later on. So let's put the boundary condition, okay. So what is the boundary condition? So let's say the beam is like this. So this is your beam. Here it is P. Then there is a in between like this, and there is a point over here. So this is actually your beam, right? Now what is the boundary condition? So this in this direction you are taking x. So this is your x equal to 0 and this is your x equal to 4, right? So the first condition of boundary if I apply, so you see this is actually what? This is actually fixed end. So due to the load, what will be the slope at the fixed end? dy by dx will be equal to 0. Cantilever end, we have understood earlier also for a simple cantilever problem, no change. So dy dx will be equal to 0. So the condition over here is at x equal to 4, your dy upon dx will be equal to 0. Is it clear? Correct? So put the condition. So you get one equation. Or you will find out something. So at x equal to 0, dy dx equal to 0. So I put dy dx equal to 0. So ui equal to 0. So this will become equal to 0 minus equal to px square by 2. So what will happen to px square? If x is equal to 4, x is equal to 4. So what will happen to p? So it will be p 4 square by 2, right? Correct? Next will come minus this 6 is cancelled, right? So x का value कितना बैठाएंगे? 4 minus 1 whole cube by 3. Whole cube. 4 minus 1 whole cube, right? Correct? Next what will be the value? 4 minus plus 4 minus 3 whole cube or whole square. Now whole cube. Correct. Next minus 2.5 4 minus 2 whole square plus C1. Is it clear? Have you understood? Just we are putting the values. Now, is there any Macaulay factor coming here? No value is coming negative, you see. In this case, no value is coming negative. Why? Because you see all the values 4 minus 1, 4 minus 3, 4 minus 2, all are positive. So if all the values are positive, then what will I do? We will have to calculate. No way I will be able to put it, right? So calculate. So calculate the value, please. So 0 is equal to p 4 square by 2. This will give you 8p. Calculate करो सब लोग. So 4 4 just 16. 16 divided by 2 8 minus 4 minus 1 whole cube. How much it will come? 4 minus 1 3 cube 27 minus 27 plus 1. How much? 1 minus 2 square into 2.5. It will come 10, right? So it is 10 plus C1, right? So what will be the equation now? So 27 minus 10 minus 37 plus 1 minus 36, right? So it will come 0 is equal to 8p minus 36 plus C1. Is it clear? Have you understood? So what will be the value of C1 then? So C1 is equal to 36 minus 8p. Have you understood? Clear? So C1 is now having a value of p. So we'll have to find out the value of p. And C1 is having a value of p. You understand? So what will happen? I want to put back the equation, value of C1 into the equation. So if I put back the value of C1, then p is again unknown. So you see, here unknowns are how many? There are 3 unknowns. Please try to understand. There are not 2 unknowns. There is one unknown C1, there is another one unknown C2, and the third unknown is P. So I will have to have another one boundary condition or another 2 boundary conditions. So first boundary condition we have put, and using the first boundary condition, what is the equation I have got? So we have solved it, and we have got C1 is equal to 36 minus P. Are you clear? So I am erasing it, okay? So first boundary condition I am erasing. You are clear on this and minus 8 sorry. So it will be minus 8. Okay? Next boundary condition. So next boundary condition, you see, next boundary condition I can put at x equal to 0, y should be equal to 0. It is a prop end. It is not a cantilever beam. It is not a pure cantilever, it is a prop cantilever, right? So at this point, as there is a support, there will be reaction coming. But what will be the displacement? Displacement should be equal to. So the next condition will put at x equal to 0, y is equal to. So I can put back over here. X equal to 0, y equal to 0. Put it in the equation. So at x equal to 0, y equal to 0. So if I put it over here, this will become equal to 0. This is how much? 0. So this will become 0 minus 1 to the power 4. You get the benefit of Macaulay method now. 0 minus 1 to the power 4. Negative. What will be the value? 0. Second term gives you 0. Third term 0 minus 3. Negative. 0. Fourth term 0 minus 2. 0. Fifth term C1x. What is the value of C1? So you should put the C1 value. So what is the value of C1? C1 is 36 minus 8p, right? Multiplied by 0. So this will give you 6. Plus C. What is the value of C2? Got it? So C2 becomes C. So see the benefit and beauty of Macaulay's assumption and Macaulay's method. When we are considering double integration method along with this Macaulay's assumption for putting the value, you see how simple it is to calculate the value of the second integration process. So this will give you C2 is equal to C. Clear? Have you understood? So this will finally land me up in 2 equations. So one equation will be this one. So this 6 and all I am removing. So this is actually 2.5 x minus 2 whole square and plus C1. This plus C1 is what? This plus C1 is nothing but your 36 minus 8p. So 36 minus 8p. Correct? 36 minus 8p. Have you understood? Is it clear? This equation becomes what? This second equation becomes what? This C2 becomes equal to 0. So C2 vanishes from the equation. And C1x is how much? C1x is 36 minus 8p into x. So this is the final slope and deflection equations after the constant of integration you have put back into the equation, right? So now you see, still we haven't got the value of P. My first aim is to find out what is the value of P, right? So what will be my third condition? So I have to put another one boundary condition in this equation. Then only I will be able to solve it, right? So considering the third boundary condition, you see, third boundary condition is another one very simple boundary condition, fixed end. So at the fixed end, slope is equal to 0 as well as the deflection will be also equal to 0. And you see, when I consider deflection equal to 0, at the fixed end, then you see, y will be equal to 0 and x will be equal to 4. And you see, if I go in this equation, then you see, you will be putting the value of x and you will be having only one unknown p in this. And you can find out unknown p on that. Have you understood? So what should be my third boundary condition? Third boundary condition, you put it is nothing but at the fixed end. So at the fixed end, where is the fixed end? Fixed end is at x equal to 4 meter, right? And at that point your y should be equal to 0. This is the third boundary condition. Clear? Or are you clear on this? What is the third boundary condition? See, you have found out C1, you have found out C2, you have got the equation of y, you have got the equation of dy dx, right? And you see, in the equation of y as well as in the equation of dy dx, you have unknown like p, because x may be known to you, but you still not know what is the value of p. So you have to find out what is the reaction at the prop end. And what is the reaction at the prop end? The reaction at the prop end is P. So to find out that, you need another one boundary condition. And that boundary condition, simple boundary condition, you see, at the fixed end, what will happen? Because of this load, when the end is fixed or it is built-in end, that is what is called, right? So at that, the deflection pattern will be like this, right? So the deflection will be something like this. That means here the slope is 0 as well as the deflection is 0. So at x equal to 4 meter, the deflection y should be also equal to 0. Clear? Now if I put that condition back into this equation, so you please put back in this equation. You do it yourself. So if I put y is equal to 0 over here, then what will come? So ei into y, that will equal to 0. Next. P into 4. So P is there in this equation. So P into 4 cube by 6. One term will come. Next will be how much? Minus 4 minus 1. Right? 4 minus 1 is how much? 3. So 3 to the power 4 by 4. Correct? Plus 4 minus 3. How much? 1. So 1 to the power plus 1 to the power 4 by 4 minus how much will come? 2.5 by 3, right? X minus 2. X minus 2 means 4 minus 2. So 2 to the power 3, right? So 2 to the power 3. 2 to the power 3, right? Clear? Plus, you see, don't miss out this term, huh? 36 minus 3, 8p, right? 36 minus 8p into. Now you simplify this. So in this equation, now you see, in this equation you have only one unknown, that is p. So you will be able to find out p from this. Have you got? So what will be the value of p? So 0. This will be equal to 0. So p 4 cubed by 6, if you do, you will get 10.67. So it will be 10.67 p minus, this will be 3 into 3 to the power 4 divided by 4 will give you 20.25. Okay, this will give you 20.25. This will give you plus 0.25 minus 2.5 2.54 minus 2 whole cube by 3. This will give you 6.66 plus what will come? 36 minus 8 into 4, right? 36 minus 8 into 4. So 36 into 4 will give you 144 minus 32. Clear? All of you are with me? Simple algebraic equation solving we are doing. Just we are calculating the value of t. Putting back the value of x, considering a third boundary condition at x equal to 4, the deflection value at the built-in end or the fixed end will be equal to 6. That's all. Okay? So now if I do it, then what will be the condition? You tell me. What will be the value of p? Can you calculate? So 32p minus 10.67p, that will somehow give you 21.33p. Okay? So you will get 21.33p is equal to, the value will come is equal to 117.34. If you simplify this, 117.34. Please try to do it. Got it? All of you have got it? So now the value of p will be how much? P will be 117.34 divided by 21.33, and that will be equal to, that will be p is equal to 5.5, right? This is coming 5.5, approximately 5.51 or something like it will come. So you take it 5.5. So what you have done? You have found out the reaction at the problem. So see, considering the deflection equation, considering the double integration method, and with the application of Macaulay's method specially, you have found out the value of the reaction at the prop end of a prop cantilever, which is actually not a determinate structure but an indeterminate structure. So you see how beautifully the deflection equation is being used to find out the indeterminate reaction component of a structure. And that is what is the task of this problem, is to understand that while solving the indeterminate structure, when you will be learning it in your 5th semester for solution of the indeterminate structure, this deflection equation not only is in double integration only, you will learn many other methods like conjugate beam method, moment area theorem, then Castigliano's method. All these methods will come into picture. Okay? So using any of the method, you can find out the deflection, and then if you can apply the compatibility condition at a particular point, then you should be able to find out the indeterminate component or indeterminate reaction component, which are in terms of structural mechanics term called redundants. What are they called? Redundant. So redundant forces, which you cannot find out using the equation of Steiner. That you can find out using the deflection conditions. So this is the applicability of deflection finding in the method of structural analysis or in case of beams. Have you understood? What is the time now? So the next part I give it to you. Okay, you do it. Even I have shared the handout with you. In that also the solved problem is there. In the canvas I have shared. Okay, so in the canvas module you can see this problem. And the next part is where will be the value, where will be the bending moment maximum, right? And what will be the value of the maximum bending? Okay, so where will be the bending moment maximum? So the bending moment, you see, the bending moment maximum will be somewhere, because you see, this load is nothing but 5.5, right? So this is going to create some bending moment at this section, as well as this UDL will create. Okay. However, once you cross this point, then you see there will be a nullifying effect of this. There will be a nullifying effect of this. So bending moment will be maximum. You should understand from the diagram. The bending moment will be maximum somewhere here before the load. Because if you cross the load, it will nullify. Px multiplied by UDL into x by 2, and then again there will be a minus. minus this, minus point load. So if you cross the point load, your bending moment will be reduced, right? So the maximum bending moment will come somewhere before the what is called the point load. Okay, and this can be very easily found out if you remember the theory of bending moment, where you have learned about shear force also. So if you have seen from there that the bending moment becomes maximum where the shear force equal to 0. Bending moment becomes maximum where the shear force equal to 0. So this condition you should apply over here to find out what is the point or the location of maximum bending. Have you understood? So shear force, let's say, what is the shear force at a distance x? So I will take a section x from here, and this section x should be before the point load. Please try to understand. Before the point load. Okay? So if I take a section at a distance x, what will be the shear force? So you see the shear force will be nothing but, so if I take 5.5 upward as positive minus, how much will be the shear force due to this? So this is actually 6 kilonewton per meter. And how much is the distance from here? This is 1 meter. So this will be 6 minus 1. 6 minus 6 into, this is actually x and this is 1. So how much is the load? How much is the distance? X minus 1. So 6 into x minus 1. So for maximum bending moment, this will be the formula. Everyone is clear on this? Why the maximum bending moment is happening before the point load? Have you understood? Because as soon as you cross the point load will create another one, reverse direction moment, which will reduce the bending moment, right? So that is why bending moment will be maximum somewhere between, somewhere before this point. And if you solve this, you will get a value of x equal to 1.917 meter. And if you put back this x into 9.71 meter in the moment equation, then you will get the value of that. So I stop here today, and please go through the handout material, whatever I have shared. Okay, everything is there, and the next tutorial is going to come for this 3 to 4 problems I will give of different flavors, and you please try to solve those tutorials also. So tutorial number 4 will be related to deflection calculation of these. Thank you. Okay.